its auroras, and they're spectacular to watch. Jupiter's auroras are like 1,000 times bigger. So the auroral oval on Jupiter is bigger than the entire Earth and much, much more powerful. And it's always on, but it's much easier to look at it in ultraviolet wavelengths because we can see it on the day side as well. When we see light from those different colors in the UV, they tell us different things about Jupiter's upper atmosphere and the particles that are causing the auroras to happen. We'll be able to contrast how auroras work at Earth with how they work at Jupiter. And there are many differences we already know, but there's a lot of things we've never been able to see at Jupiter that we can see with Juno once we get there.
The WAVES instrument is basically a radio. It tunes to frequencies all the way from 50 hertz, which is near the bottom of the audio frequency range, up to above 40 megahertz, which is above the limit of the radio emissions that Jupiter generates. The WAVES instrument has two sensors. One is designed to measure the electric field component of these waves, and it looks like a pair of rabbit ear antennas that you might have had on a TV when you were a kid, except these are about 10 feet long. The other sensor is a much smaller device. It's about 10 inches long, and it's basically a coil of wire. It has about 10,000 turns on it, and it's designed to measure the magnetic fluctuations of waves. So these two sensors are used by the receivers to study the various phenomenon, particularly in Jupiter's polar magnetosphere. For example, the maximum frequency of the radio emissions that we detect told us what the magnetic field strength was in the magnetosphere of Jupiter, long before any spacecraft arrived. Juno was designed to actually go to another planet and make the first measurements of an extraterrestrial auroral region in great detail. So I think we learn about ourselves by studying other environments in the universe.
ATLO is an acronym. It stands for Assembly, Test, and Launch Operations. Basically, we'll assemble it, and we'll do all the system level testing, we'll do all the environmental testing, we'll do all the launch processing, and then we will go ahead and launch it.
So in ATLO, you basically start with a bunch of pieces. We had what was known as the prop module. That's the large base piece of the structure. On top of the prop module sits the vault. Individual boxes, flight computers, our power subsystem, all came in separate pieces. And in ATLO, our job is to take all those pieces and come up with a plan and strategy of putting them together in an organized manner that makes sense.
We have a philosophy at Lockheed Martin to test as you fly. We have to try to replicate the environment that the spacecraft is going to see in space.
So we basically trick it through another piece of software into thinking that it's flying. And so we run through all these scenarios just like in flight, and we verify that it functionally does what it's supposed to do.
So in order to accurately represent all different environments that the spacecraft is exposed to, we need to kind of break up the tests individually. One of the more exciting tests that we got to run on the spacecraft was the solar array deployment test. We had very large solar arrays on this spacecraft so that once we get to Jupiter, we have enough electricity to operate the spacecraft. In order to be able to deploy them with low friction, we used a flat floor and a pneumatic device that's kind of like a hovercraft. A thermal vacuum test is probably the largest, most thorough, complete test that we'll do on a whole entire spacecraft assembly. So once we get the spacecraft fully assembled, we will put it in a large chamber that tries to replicate space. Also within the chamber is a shroud that is filled with liquid nitrogen, and it can get as cold as negative 180 degrees C. So we try to simulate what environment the spacecraft is going to experience in space.
So we get through these major environmental milestones, verify that the spacecraft is working as we planned, take it out, verify that it functionally works after we do all the tests, then we prep it to ship down to the launch site.
On launch day, of course, it's a dream to have perfect weather, no clouds in the sky, but we have to do with what we have. There are weather rules in place, weather criteria that we cannot violate. There are rules for cumulus clouds. There are rules for anvil weather clouds. There are rules for lightning within the area, within 10 miles, within 5 nautical miles. So there are several weather rules in place.
Atlas systems, propulsion, go. Hydraulics, go. Pneumatics,
Making
go.
a list to get through a launch countdown is the only way to get through a launch. And even once my list is checked off, I still won't throw it away because I want to go back and double and triple check to make sure that I did everything on that list.
As soon as we get the go-ahead from ULA, we will power up the spacecraft for the final time. We make our spacecraft dirt simple, so that at the end, there's very few things to go wrong in this very critical time. So our spacecraft is a very easy spacecraft to launch.
Juno gets to Jupiter by flying by the Earth. It gains momentum by passing the Earth at 500 kilometers altitude, and in doing so, it gets sucked into the Earth's gravity well. And what happens is that the trajectory, which is on a path relative to the Sun originally, now is flying by the Earth and is also influenced by the Earth's gravity field. It gets deflected out towards the planet Jupiter. The idea is that you can't get there directly unless you have a much bigger launch vehicle. When we get to Jupiter, we do a big maneuver called JOI. The Jupiter Orbit Insertion Maneuver is what actually puts us into an orbit about Jupiter so that we're captured by Jupiter's gravity. It needs to be a big maneuver because we're flying at this enormous velocity around the Sun, and in order to be captured by even a big planet like Jupiter, we have to aid that capture by doing a big maneuver to slow us down. There's so little time to react that we have to let it do its own thing and just trust that the planning and the testing that went into that will do the right thing. We plan on actually listening in on the spacecraft as it does its Jupiter orbit insertion. And at the very end, we have it radio back to tell us, okay, we did all the right things. Here's how the spacecraft is doing. We survived.
One of the great excitements about space exploration is it's a big public endeavor. Everybody's involved.
There's some wonderful amateur astronomers who are very knowledgeable about individual storms and clouds on Jupiter.
I think the public involvement in these missions are really what makes it important and exciting and fun. If it was just us scientists looking down our own microscope, it wouldn't be so much fun.
The public will see how we make decisions and what we care about.
They'll continue interest in science, they'll ask questions, they'll be curious. I think this is an important part of society to think about what's out there and how it works and how it all fits together.
Not only do our capabilities complement each other, but our enthusiasm infects each other, and it's a very good collaboration with the amateurs.
I, as a 14-year-old, stayed up until 4 in the morning to watch the guys walk on the moon. And I expect there will be kids who will be following everything that's happening with Juno. It's a great privilege to be involved with something where the public are all actively interested. Yeah, it's fun.
This is Atlas Launch Control. We are now 2 hours, 32 minutes, 32 seconds away from the liftoff of the Juno spacecraft aboard an Atlas V rocket. Liftoff is from Launch Complex 41 at Cape Canaveral. The forecast is essentially unchanged from what we've been watching all week. There is just a 30% chance of not meeting the launch weather criteria.
It takes everything we know to get off this planet. So while everything that NASA does and building the Juno spacecraft and exploring Jupiter is all high tech, I think a rocket launch represents the extreme of that edge.
The energy in the room on launch day is stressful, but in a good way. It's a good feeling. It's almost electric. Everybody's excited and nervous, and I've seen people before, biting their nails.
A rocket launch is one of the most amazing things to see it. I mean, it's truly a cosmic event.
Go. ULA safety officer. Go. Range, weather, and final clear to launch. Go. LC, LD, Channel 1.
Go ahead.
LC, you have permission to launch.
Roger.
The launch is probably our single biggest risk in the entire mission.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Atlas V with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system.
When you see it, the first thing that you're impressed with is just the amount of energy. You feel it because the ground is shaking and you're miles away and the waves are coming through the ground like an earthquake would.
Mach 1.
You're canceling gravity. Gravity's pulling you down. You've got to get to a certain speed, and then that's the escape velocity to leave the Earth.
Max Q. Boosters throttling up. We're on schedule. Engine response looks good.
You're watching something going from one planet to another.
And we have solids 1, 2, 3, 4, and 5 jettison. Visual indication that all solids are separated well. Current altitude is 45.8 miles. In altitude, downrange distance 69 miles. Velocity 5,413 miles per hour. And we have payload fairing jettison. And CFR jettison. We have retros and spacecraft separation. This concludes the PlusCom commentary for the AV-29 Juno mission.
We communicate with the Juno spacecraft with radio waves and radio frequencies. But what we do is we send up commands or data to the spacecraft to tell it what to do. It in turn takes data and sends back what we call telemetry.
The way that we find out if there's a problem on the spacecraft in space is by monitoring our telemetry. And our spacecraft talks to us on Earth through the Deep Space Network.
The Deep Space Network is a set of antennae that we use that are around the world in order to return data to us and to send commands up to the spacecraft.
We've designed a lot of points on the spacecraft that tell us things like the state of charge of the battery and what temperature things are at. And we look at that telemetry and monitor if the spacecraft is happy or sad and doing well or not. And we set limits on that so it will give us automatic alerts if something's wrong. And so on the ground we can look at it and make sure everything's okay. We can detect a problem that way. The primary way that we detect problems on the spacecraft is we make it smart enough to detect them on its own. So the spacecraft has a system called fault protection.
It's constantly looking for how the spacecraft hardware and software is operating. Is everything going per plan? Do we have anything that's not operating as expected?
So if we're spinning and the spin rate gets out of control, a fault protection is looking at the spin rate and determining, okay, this level of spin is okay, and if it gets past this number, I'm not happy. And so if it gets to a number that it's not happy, it will take action.
It actually will take care of it itself, and then after it's reconfigured or whatever, then it'll send down information and let us know that that's what's happened.
Or if it can't solve a problem or the problem is too large, it will put it in safe mode and basically say, okay, I'm just going to wait for the ground to help me because I'm confused.
Nothing should cause a further problem for the spacecraft. We shut down the instruments, we shut down other aspects of the spacecraft, and we make it kind of operate very simply at a very low data transfer level so that when the Earth picks it up, it's very apparent to us right away that it's had a problem, and we can then start fixing it right away.
The spacecraft would continue to operate after it experiences a particular fault. One particular fault will not result in a total failure of the spacecraft.
Our little spacecraft these days are very complicated and they're very smart. They know how to take care of themselves.
So in a lot of ways, the most innovative or dramatic thing about Juno is the orbit. We're going to orbit Jupiter in a way where we get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that Juno is going to see the polar regions to a greater extent than with other spacecraft, but I think the most important thing is that it gets in very close to the planet as part of that ellipse, brings it in a few thousand miles above those cloud tops, very close, near the equator.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way, where all the magnetic field lines come together, we get to see from Juno. This is the first time we're really using passive microwave radiometry and multiple channels to try to study the composition of an atmosphere, especially a giant planet like Jupiter, and that's new and unique. But in some ways, the most unique part of the Juno mission, the thing that really makes it stand out, is just the orbit.
An aurora, as we see it on Jupiter or on the Earth, is caused by charged particles, electrons or protons, crashing into the atmosphere.
When those electrons come bombarding in, they excite the electrons inside the hydrogen atom, and UV light comes pouring out, and that's what produces most of the aurora on Jupiter. This is very similar to the northern lights of the Earth. It's the same physical process.
Deep inside the planet, the hydrogen has been compressed so much that it loses its electrons, and you have a conducting layer. So people call this metallic hydrogen. And it's in that conducting shell that we think Jupiter generates its magnetic field. Now, one of the interesting things is that it's carrying with it electrons and protons that are spiraling around as they crash into the atmosphere at the north and at the south. And when they do that, they create what we call an aurora because they're generating light. It's quite a spectacular sight if you can see this aurora going on. It's so bright that you don't have to be on the surface of the planet where this is happening. You can look at it from the outside. And Juno is equipped to look at the aurora on the north and south poles of Jupiter and to study it in a way that has never been possible before.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it.
The presence of the Earth's magnetic field was recognized back in the 14th or 15th century, and since the 17th century, it's been a topic of active study. Yet we still don't really know how magnetic fields are generated inside planets.
The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter. So this is vast, a big, big, big volume.
By measuring Jupiter's magnetic field from Juno, we hope to do two things. One is to advance our understanding of how magnetic fields are generated in planets, and the other is to learn about the interior structure of Jupiter. You might question why go 400 million miles to Jupiter to study its magnetic field when the Earth has a perfectly good magnetic field which we could study. Jupiter's metallic hydrogen core is much closer to the surface, so when we measure Jupiter's magnetic field from Juno, we're much closer to where the magnetic field is generated, and by looking at the magnetic field, we should be able to tell whether Jupiter has a solid inner core, and that has profound consequences for how Jupiter formed, for models of its interior, for understanding its gravity field. It's a sort of key observation we'd like to pin down for Jupiter.
The rings of Saturn are very well known. They're this gorgeous set of rings circling the planet. These rings are made of ice crystals, and that's one of the reasons that they're so bright and that they're so easily seen. It turns out that Jupiter also has rings, but these rings are made of dust, so they're hard to see. In fact, they were only discovered by the Voyager spacecraft. Before that, we didn't know that Jupiter had rings. They're caused by small satellites that Jupiter has moving around the planet close in. These satellites are releasing some dust from their surfaces, and that dust forms the rings. That's why they're so difficult to see from the Earth. When you get close up with the spacecraft, they're obviously easier to see. You might worry about Juno running into some of these rings as it makes its orbit, but it doesn't. The orbit is oriented in such a way that it will not pass through these rings.
The reason we plan to crash Juno into Jupiter at the end of the mission is for what's called planetary protection.
We can't make the spacecraft perfectly sterile. We try to keep it as clean as possible. We spend quite a bit of effort, dressing up in bunny suits and putting in a clean room that's changing air as fast as we can do it and trying to keep it as clean as possible, but nothing's perfectly clean.
The United States is part of an international treaty that says we will be sure not to contaminate other worlds that could potentially harbor life.
There are some moons around Jupiter and Mars and other places that kind of look enough like Earth that we're thinking, well, maybe there is a life that we would recognize there.
You would really hate to, 50 years from now, send a mission to, say, Europa, one of the moons of Jupiter, and find life and then not be able to tell whether this is Europan life or contamination from Juno.
So what we do is we dispose of Juno when we're done with it, and we let it burn up in Jupiter's atmosphere.
There's about a 99% chance that what would eventually happen to it is it would crash into Jupiter, burn up, not contaminate anything. But 99% chance isn't good enough for us. It isn't good enough for NASA. We need to show by agreement with NASA that we have a less than 1 chance in 10,000 of contaminating Europa. So while we still have control, before the radiation has done any damage, we'll fire the rockets, we'll burn Juno up in the upper atmosphere of Jupiter, and that way we'll be certain we're not going to contaminate anything.
Jupiter has such a strong radiation environment that when we send all our sensors in to do their observations, there's a lot of challenges that have to be overcome to make sure that they can do that, particularly with noise. All the high-energy electrons and protons in the environment whiz through the instruments and create noise in the detectors and sensors. That kind of condition can be a catastrophic event for a device. It can destroy it. So that's one of the radiation effects that has to be screened and understood when you're designing an instrument. Testing for the Jovian radiation environment on Earth is not easy. You have to go to a very high energetic electron facility, which is a very rare type of facility on Earth for this kind of testing. It's not something that's commonly done. People don't do space missions to Jupiter very often, so there isn't a big customer base for that. We've ended up going to facilities and hospitals that treat cancer patients, or other facilities that are used to simulate nuclear blasts for submarines. Very unusual places in all different parts of the world in order to mimic the Jovian radiation environment. Right now, we're looking at how we can understand what the environment is actually doing to our instruments while we're in flight. We've modeled it, we've tested, we have a good idea of what will happen, but we can understand from the instrument telemetry and the science return exactly what they're experiencing. If there are certain failures or graceful degradations, that will be visible in that data stream coming down. The very extreme radiation environment, very changing radiation environment, and other missions in the future will go to these locations and they will design based on what we'll be learning.
The short answer for why Juno is solar powered rather than nuclear power is because we can. At the time we did the proposal for Juno, NASA had generally speaking, a policy that it's okay to use nuclear power to do things in space where you need to use nuclear power. But if you can do something simpler like solar panels, you should.
We decided it was probably less risky to advance the technology of solar cells to work at Jupiter than it was to invent a new nuclear power source.
We haven't taken solar panels that far before and run an entire spacecraft that far from the sun off of solar power.
We had to work at a colder temperature. We had to work with less light, and we had to be able to work inside of a radiation environment. So as things got damaged, you had to either protect them or make them more efficient.
The biggest design challenge of the solar arrays was probably just their size. Each solar array is 28 feet long, and so we have 3 of them. And so when the solar arrays are fully deployed, the Juno spacecraft is almost 60 feet in diameter across the solar arrays.
Getting those big solar panels to work the way we expect them to work and produce the amount of power we need, that's been a bit of a challenge.
The solar arrays are pretty interesting. When we deploy them, they'll be generating about 12 kilowatts of power. As we get further and further from the sun, that amount of energy will drop off until we finally get to Jupiter, where we're only generating 400 watts. It's not even enough to run a hairdryer.
Generally, with space exploration, you're pushing the envelope of technology.
Solar panels have improved a bit. The instruments have improved a bit and can run on less power, and I think it's turned out to be a very good decision for Juno.
The design of Juno and the science measurements that we wanted to make were all taken into consideration at once when we were trying to figure out how to do this the most efficient way. So Juno has 3 solar arrays that stick out. It could have had 4 or 5 or any number. We looked for something that was efficient and could be packaged inside of a rocket. That was one of the first requirements. We also wanted to carefully make it so that the science instruments could look out between the solar arrays. We knew we were going to have to see a certain, what's called a field of view. I wanted to be able to look up and down the magnetic field lines as we flew over Jupiter so I could see the particles that were creating the aurora.
When we come off of the launch vehicle, we're spinning at about 1.4 RPM. When we do our burns, we spin up to about 5 RPM to give us a little more stabilization. And when we're going around the planet, we're spinning at about 2 RPM.
Juno spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered, and we want to have each of the instruments to be able to look out between the solar arrays and see Jupiter or wherever they need to look in order to do their science objectives.
There's 2 basic reasons why we want to have a rotating spacecraft. One is really simple. It's just stable that way. If you spin something, it stays spinning. It's like a gyroscope. We call it a simple spinner, a spinning spacecraft. The other reason is we can use a spinning spacecraft to let each instrument get its turn to see Jupiter.
If I had only one sensor looking in one direction, because I was spinning twice a minute, you'd think I'd be able to look in all directions every half a minute. But I'm moving so fast going over Jupiter that in fact I'm going to pass the field lines that are making the aurora, and I might only be looking up or only looking down or looking sideways by mistake. And so by putting 3 sensors around, looking all the time between the solar arrays, we ensure that no matter how fast we go across, we're looking in the right direction to make our measurements.
Once the whole spacecraft gets put together, it's important for us to operate it in a flight-like way. So we enact a policy on our missions here at JPL called Test As You Fly. We say, okay, we're going to pretend that we're launching the spacecraft today, and we set the universe simulator in the clean room to pretend it's launch day.
Juno has a very complex instrument suite. The instruments are tested both individually at their home institutions as well as part of the flight system on the path towards launch.
We try to replicate both the conditions, the timing, the personnel, the procedures, the products, the hardware, everything, similar to what we would have actually in space when we're flying.
We will go through acoustic energy testing to make sure that the instruments will be able to withstand the launch environment. We'll go through a thermal vac test where we'll simulate being in a vacuum in space.
We pretend to fly the mission on the ground, and then we make sure we understand the differences between the environment we have on the ground and the environment we have in space.
It's a blast to march through that testing suite and make sure that you've thought of all the contingencies and tried to break it and make sure it's going to do what it needs to do.
What is the Great Red Spot? It's a swirling mass of gas and colored clouds that is bigger than the Earth. It's been around since the telescope was invented. Maybe it's much older than that even. People sometimes call it a hurricane, but it's probably different from a hurricane in the way it works. There's no ocean underneath, and it's much bigger than a hurricane and doesn't have any intense eye at the center. The red spot is rolling like a ball bearing between two conveyor belts. Just to the north of the red spot, there's a westward moving jet stream. And just to the south of the red spot, there's an eastward moving jet stream. Somehow the jet streams steady the red spot and keep it trapped at one latitude. There's no solid surface with which to measure your wind speed. It speeds up and slows down slightly. It's not anchored to anything. It's on its own schedule.
The interior of Jupiter is a tough problem for us. To get deep inside, we have to use indirect methods. We can't go there.
We think that Jupiter has a core, but we don't know for sure. It is nonetheless likely to be perhaps 10 times the mass of the Earth. It may not be solid. It's very hot.
The pressure is too great. The temperature is too high. It's just too far in. We can't get there. So what we have to do is to use radiation that's coming to us from those lower depths to tell us what's going on down there. And this is where Juno comes in.
Juno is exciting because we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
What is the proportion of water on Jupiter compared to the amount of hydrogen on Jupiter? And how does that compare with the proportion of hydrogen to water in interstellar space and in the sun? That's a very important question, and that's one of the things that Juno is going to address directly.
I would expect Juno to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated, learning what Jupiter is made of, and learning about how it works. Those, to me, are what make the Juno mission exciting.
One of the most exciting aspects of weather is a thunderstorm. So what happens on Jupiter? We know that lightning occurs on Jupiter. The Galileo orbiter made images of lightning on the night side of Jupiter. And these lightning bolts are hundreds of times more powerful than lightning on the Earth. In a way, this is surprising because Jupiter gets less sunlight, less energy from the sun than the Earth does because it's much farther from the sun. With Juno, we want to understand the structure of these thunderstorms. We want to understand where these parcels begin to rise, how much water is in them, how they're organized, are they larger than terrestrial thunderstorms, and why it actually has thunderstorms and super lightning. Juno will be able to tell us that.
When I was younger, I was always fascinated by astronomy, and I remember just looking up in space and looking out at the stars out there, wondering what was out there.
I actually wanted to be an aerospace engineer even when I was a little girl. I really liked math, and I liked, space and astronauts, and I would write letters to the NASA centers and get pictures and stuff.
I had posters in my bedroom of Jupiter and Neptune and Saturn. I thought they were just amazing.
As a little kid, Jupiter was my planet.
I would look out there, and you couldn't touch it. You couldn't learn about it enough because you couldn't get there. And so I always had this yearning to want to reach out.
And when people would ask me, what do you want to do when you grow up? I said, I want to work on spaceships.
I really wanted to work on rockets and build things that would go into space. And
it's just really exciting to have a chance to do something that I really wanted to do when I was a little kid.
For whatever reason, I got lucky, and I'm the head of Juno. And I'm reaching out. And of course, I could never have done it myself. It's only through everybody reaching together that we can reach it all.
It started out on the back of an envelope, as many things do.
It's amazing being able to see a vague notion that you have in your brain turn into
a real piece of hardware that is going to fly all the way to Jupiter.
So Juno is really an incredible international mission. It's a very large mission, involves people from many, many different countries. Engineers, administrative people, technicians, people who do purchasing. I mean, it's amazing how many people in different walks of life have to be involved in making a mission like this happen.
It's a big public endeavor. Everybody's involved.
We really have the A-team here, and it's amazing that when you get that kind of atmosphere and that kind of collaboration and synergy.
Involved in something.
To understand our origins, how the solar system formed,
to someplace where few things have ever gone.
When you work on a project like Juno, which is really exciting, and there's a lot riding on it about all kinds of things.
In a way, it's like having a child. You rear this child throughout the years, and then all of a sudden they take off on their own and they become independent.
It feels a little like an unruly teenager that I'm ready to get out of the house.
Some of those cameras really do feel.
There's nothing like listening to that launch vehicle take off and watching something that you built and poured a lot of time and energy into. Leave it.
He holds their breath and just waits.
I think it's starting to hit all of us how close.
That will be so exciting and so different all the time, and again have such job satisfaction.
It's very rare to see a team.
And I love it.
It's such a fun job, and it's really a wonderful way to make the world seem even bigger than it is.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife, of course, was the king of the gods, and she was the queen of the gods, Juno. She was married and cared a lot about children and marriage and keeping everybody well behaved and sort of like a good mother would. And Zeus was sort of being naughty with some friends and doing things, and he saw Juno looking down at him or starting to come close to him, so he cast a veil of clouds around himself and his friends, traveled down and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
Jupiter's by far the largest planet in the solar system. It has an influence on everything else. So if we want to understand
life form, but maybe how the ingredients that made up life eventually got spread around in the early solar system and got to us.
We care about the light elements because that's what we're made of. We've got a puzzle about where these volatile elements, these lightweight elements like nitrogen, carbon, noble gases, where they came from.
To determine how much water is in Jupiter is essential to understand how this planet came to form, and then how it influenced the formation of all the other planets in the system.
When the Earth formed,
we could find these aliens not on distant planets in unexplored galaxies, but right next door in our own solar system. Scientists are now honing in on proof that ET is out there and living on the most hazardous of worlds. Might look like. These exotic lands are unimaginably harsh. Life as we think of it would perish in an instant. But alien life may be far tougher than we expect, as we're learning from a surprising group of living things right here on Earth. Until just a few decades, warm water and protected atmosphere. We logically concluded that life needed each of those things, a conclusion that ruled out all other known worlds in our solar system. But then, living, breathing creatures. Biologists call these organisms extremophiles. Some don't need light or oxygen. Others survive in tremendous atmospheric pressure. It seems life can turn up practically anywhere. Take Antarctica. Of
After years of searching this arid, frozen landscape, scientists doubted they'd find anything alive. When they cracked the rock open, they found it teeming with tiny creatures. Here, at temperatures of 68 degrees below zero and 6 feet under solid ice, life had found a foothold.
Biologists have been increasingly discovering life, not kangaroos, but, simpler forms of life that live at very cold temperatures, very high temperatures, very great pressures, even in places where there's sort of a high degree of radiation. It turns out life is able to live in a much wider variety of environments on our own planet than we used to think.
And if life can survive extreme conditions, not just here at home, but elsewhere in our solar system, think of what this could mean.
Unless there's something extraordinarily miraculous about our solar system or our planet, then life has got to be extremely commonplace. I mean, there's got to be large numbers of worlds with life, and some of them would have cooked up intelligent life.
In the beginning, our Earth was as deadly a planet as any. Over the first billion years of Earth's existence, cosmic where life was impossible. But once the solar system settled down and the Earth began to cool, water appeared, setting the stage for life. In 1953, researcher Stanley Miller proved in a lab experiment just how easily life on Earth got its start. He combined water with hydrogen, methane, and ammonia, components of the Earth's early atmosphere. Then he zapped his solution with an electric charge to simulate lightning. His results shocked the world. Miller had created organic molecules called amino acids, the protein building blocks of all living things. If lightning helped jumpstart life on Earth, could it have done the same on other planets? Galactic probes have now found the ingredients in Miller's experiment throughout our solar system, including one essential to life.
We've used evidence for liquid water to kind of guide our search for habitable environments.
Our safari is headed to 7 worlds, some possibly rich in water, where scientists believe aliens might be hiding. While any life there might have begun much like life on Earth, how it looks now is anyone's guess. We begin in the world that has always fired our imaginations, the planet right next door, Mars. Of all the planets where we've looked for life, it's the one we've studied most. The science.
Mars has always had, among all the planets, I think, a special fascination for humans. For a very long time, we've known enough about Mars to know that it is probably the most Earth-like.
It may be the most like Earth, with an atmosphere and seasons, but we humans would perish quickly on Mars. Its air is thin, 40 times thinner than the air at the top of Mount Everest. And it sits in a bad neighborhood of our solar system, near an asteroid belt. Its atmosphere is too flimsy to protect it. Asteroids and spawn tornadoes 8 kilometers high. Midday temperatures of the equator. Spoon is a curator of astrobiology at the Denver Museum of Nature.
It's going to cool off quickly, whereas a larger coffee is going to stay warm much longer. Large objects, a larger planet like Earth will stay warm for billions of years, which makes it a better.
Terrain seem to give evidence that it might support life. Its dynamic landscape of mountains, volcanoes, and deep ravines is not unlike our Earth. To early astronomers, these features look like oceans and rivers, and even
observed these things and inferred that, in fact, these things were so straight and so visually through a telescope eyepiece, the human eye-brain combination started to connect things that weren't really there.
Lowell was not alone. Some scientists were shocked when the probe Viking 1 beamed back this image. Is that a human face? Perhaps produced by Martians in their own likeness? Life. But we've always known what the aliens would be like once we found them.
I was on a table.
Images of ourselves. As a senior astronomer at the Search for Extraterrestrial Intelligence Institute in California, Seth Shostak has spent his career listening for the radio waves of a distant alien society.
There's no reason to assume that they're going to look like us or even think like us or behave like us or have language. You know, you just have to look at the variety of life on Earth and you see that, you know, nature can come up with lots of different forms.
But if there is life on Mars, how could it survive in such extreme conditions? Since the 1960s, scientists have sent dozens of probes to the Red Planet. The first pictures of the barren landscape quickly dashed any hope of finding intelligent beings. They may have had water. Some think the angry red planet might once have been blue.
You just have to look back a couple of billion years, 3.5 billion, 4 billion years ago. Mars had a thicker atmosphere, had water on its surface clearly. Maybe it developed life. And as it slowly went bad, you know, the life had to adapt.
Life may have adapted, not died off, because some liquid water may still exist underground. But with no surface water, frigid temperatures, and ultra-thin atmosphere, Mars is a planet only one kind of creature could love, an extremophile. Extremophiles thrive in the cruelest of places. To see where they might lurk on Mars, we head to the Valles Marineris, a massive rift in Mars's surface, 20 times wider than the Grand Canyon in places, and almost as deep as Mount Everest is tall. Lakes may have once flooded this valley, and those lakes could have hosted life. As the water dried up, life could have evolved to cope with the harsher environment. We won't know what these extremophiles are like until we find them. But they may resemble creatures that exist in extreme places right here on Earth. An unusual team of biologists, called astrobiologists, study Earth for the kinds of life we may find in outer space. Astrobiologist Rocco Mancinelli is on the hunt for Mars's extremophiles.
If it went beneath the surface, and some of it undoubtedly did, then what happened to it? Well, it formed brine pockets. So what kind of organism can live in a salty brine? A salt-loving organism.
Astrobiologist Chris McKay thinks he knows the kind of salt-loving creatures that might survive on Mars. Creatures much like those he's found in one of the driest, saltiest places on Earth.
The fundamental challenge to life on Mars is, in a sense, the fundamental challenge of life here in Death Valley. It's dryness. That is the hardest thing for life to adapt to.
Thousands of years ago, a salty lake covered Death Valley, just as lakes filled Mars's Mariner Trench.
Moving closer. This is still wet, a little wet. This appears like a lifeless place, a big, flat, white, empty horizon. But yet, just below the surface, we find layers of algae and bacteria growing. They're living in an environment that in many ways is fundamentally different from the environment that we sense on the surface. Here you're in a place which looks lifeless, looks dead, and yet you dig down and hidden underneath, there it is.
Beneath the salt is a layer of hardy green algae that survive on the water and light that trickle through. The algae in turn feed salt-loving microorganisms.
Here in deserts on Earth, dried, salty lake beds, we're going to find them on Mars as well.
Salty deserts are not the only places life might be hiding on the red planet. There are Mars's tremendous volcanoes, some of them 6 times larger than those on Earth. Astrobiologist Penny Boston studies the caves, called lava tubes, left over after volcanic lava has dissipated. Not long ago, we assumed caves like these were devoid of life. They get no sunlight, and no sunlight means no photosynthesis. But in lava tubes outside Albuquerque, New Mexico, Boston has found evidence of extreme life.
Because we know Mars has many, many lava tubes. And so here we have the opportunity to see how these formed and also to look at the life that inhabits them.
The extremophiles Boston has found appear to be thriving. They get their energy by feeding on the minerals in the cave wall.
So here we're up close to the wall, and you can see these white patches here growing against the black basalt. And each one of these is like a major city for these little guys. They're all nestled in these little pockets in the basalt. And so these guys are permanently adapted to these freezing temperatures. They never see any light, and they get what they can find in the environment.
Are there creatures like these in the caves below Mars's volcano fields? Boston thinks so.
We are going to find life, and I just hope that I live a long and healthy life so that I can still be around to see that.
We may already have had our first glimpse of Martians, not from our visit to their planet, but from their visit to ours. 16 million years ago, an asteroid slammed into Mars and propelled a 2-kilogram rock into space. Amazingly, that rock sailed to Earth and came to rest in Antarctica. Inside, NASA scientist David McKay and Everett Gibson were amazed to spot the outlines of fossils. Water has carved small tunnels in the rock. And in these tunnels, McKay and Gibson found what they believed to be evidence of bacterial life.
These are little microbes, and they're dead, and they're fossils, or in some cases, we don't even see the forms. We see the footprints or the evidence that they were there.
Life from Mars? Maybe. The hunt is only just beginning. NASA plans to send a rover called Phoenix to Mars. It will study the planet's ice cap and probe 3 feet beneath the surface. NASA even has a plan to send human visitors. They may not meet the little green men of our imaginations, but they could encounter life in some form. What will it look like? It is likely to be a subterranean dweller with an ability to survive on little water. Perhaps an organism with a taste for minerals, like the creatures in the lava tubes of New Mexico. Even the smallest find would have enormous implications. Proof that life is not unique to Earth, but exists just next door. Our safari to the places in our solar system likely to harbour alien life now takes us past the asteroid belt on the far side of Mars. Here, Jupiter reigns. But this planet, the largest in our solar system, is fairly hostile to life, thanks to its toxic gases and overpowering gravity.
Not only is it pretty cold out at Jupiter, it's also, it's got this really thick atmosphere, tens of thousands of miles thick, and it's got ammonia and methane and things you use to clean the bathroom. But Jupiter has more than 60 moons that we know about.
At first glance, those moons would seem unlikely places to seek alien life. Their atmospheres are thin, and they are inhumanly cold. The temperature on Callisto is lower than minus 200 degrees Celsius. The scientific probes Voyager and Galileo have detected little on the surface of these moons but ice, with one dramatic exception. Io is one of the closest moons to Jupiter. When NASA sent Voyager 1 to Io in 1979, astronomers were astonished to find its surface roiling with giant volcanoes.
Io is the most volcanically active place in the solar system, just spewing volcanic material from its surface all the time.
What could be heating the interior of this frigid moon? Amazingly, it's the force of gravity from Jupiter. The giant planet exerts enormous gravitational pull on its moons. The closer the moon, the stronger the force. So strong, it can actually stretch their crusts. But some of these moons have elliptical orbits, so as they near Jupiter, the crust stretches towards it. When they move